We now reached the Z-transform. It's one of the most powerful transforms for discrete time. And we can see the Z-transform as a generalization of the discrete time Fourier transform, the DTFT. So if we recall the definition of the DTFT, we see this e to the power of j omega, which is a complex number on the unit circle. But if we replace this complex number on the unit circle by a general complex number that doesn't need to be on the unit circle, we get the Z-transform. So we are replacing e to the power of j omega by z. So in very general terms, the Z-transform is turning a sequence into a polynomial, and we could use SimPy, for example, to transform a sequence into a polynomial. So the Z-transform is more general than the DTFT, and it becomes more powerful because we can compute the Z-transform for unstable signals of systems. So that would not be possible for the DTFT because the sum would not converge. We can determine if a system or a signal has damping. So if it lies inside the unit circle, we can see if it's unstable, if there are poles outside the unit circle generating exponentially growing signals. And this is the so-called two-sided Z-transform, but when we are dealing with causal systems that has a starting point in time, we can have the one-sided Z-transform that goes from 0 to infinity. The convolution in time also becomes a multiplication in the Z-domain, so we can take advantage of this. The Z-transform is also invertible, so we have the inverse Z-transform defined by this equation here with this closed contour integral. But when we have causal and stable Z-transform, where all the poles are inside the unit circle, our closed contour can become the unit circle around the origin, and we can set Z to be equal to e to the power of j omega for omega in between 0 to 2 pi. So if we apply some variable substitution, we have that dz over d omega is equal to j times e to the power of j omega, and our Z-transform, inverse Z-transform equation, we can replace z by e to the powers of j omega. Dz we replace by this here. The closed contour becomes the normal integral for omega going from 0 to 2 pi. And we have that the Z-transform, the inverse Z-transform for causal stable signals or systems becomes the inverse DTFT, identical to the inverse DTFT. So in practice, all finite length sequences are always causal and stable, and their inverse transform becomes the inverse DTFT, which are the coefficients of the Z-transform polynomial. And we can also use Python to get the coefficients of the Z-transform polynomial. Still remembering that what is periodic in time results in discrete frequency, and the discrete time results into periodic frequency. So in practice, we always will have discrete finite signals, so our frequency domain will be discrete and periodic.